And why are you drawing on the whiteboard?
Sorry, ma'am. I was just trying.
It's fine.
Ma'am, for me, it was like disabled. For Aman, I'm wondering how it.
I'm not sure of that, but I have disabled it for everyone now. So oops. Okay, so you have been given this tree. It's huge and it's looking very huge also. You will be given root and an integer k. Okay, and you need to find out how many nodes are there at a distance k from the source node. Just a minute. Sorry, my bad. It's not like root node. Like root will be given to you obviously, but there will be some source node also given. Okay, so let's assume this is your source. So this source node will be given. Root node is already given to you, source node will be given to you, and an integer k will be given. So you need to figure it out how many nodes exist at a distance k from the source node. Are you guys able to follow? Okay, if I manually calculate it saying that k here will be equals to 4. Okay, so if you see here 1, 2, 3, 4 and 1, 2, 3, 4 also, these two. So I'll just highlight what are the nodes which will be, sorry, this highlighter is not good.
So if we go upward, root is also at distance 4.
Yeah, I'm coming on that point. Yeah. So this is the one, this is the one. Okay. After this, if you will go on the left hand side, you can't find any other nodes at distance k further. If you go on the right hand side, nothing is there. If you try to go up 1, 2, 3, 4 and 4 also. So you got another nodes, one this and one is this. Next, if you again try to go up further, 1, 2, okay, so 3 and 4 will come. Here again, you found your node. Next, 1, 2, 3, 4, you found it as this one. Another which can be found is 1, 2, sorry, 1, did I check something wrong? 1, 2, 3, yeah, my bad. 4 will come here. So root node will ultimately come. Or you can get here as 1, 2, 3, 4. So this one is also there. Any other possible node which is at distance k from the source? All are covered, right? Okay. So did you guys got an idea what we need to do in this particular question? So total number of nodes here are 7. So you need to return an output as 7. Clear, guys? Okay. Will you try to do it on your own? It is little important question. So that's why I am discussing this in the class. If you guys are at all unsure that I will not be able to do it, we can discuss it in the class. Today you want to give it a try, and tomorrow you want to discuss. That also we can do. Okay, you want to give a try? Fine. Okay, so oops. Let me just erase. Yes, guys, are you all okay with discussing this question tomorrow if you guys are not able to do it on your own? Or do you want me to discuss it right now? Tomorrow. Okay. Our next question is, we have seen so far pre-order, like printing the pre-order in a recursive manner. But have you ever thought that how to print the pre-order in an iterative manner? No, right? So that is our next question. You can found this question in the interview bit. Okay, interview bit, you go to the tree section. Just give me. Pre-order without. Yeah, it can be for loop or it can be any other looping technique. It's just that it should be without recursion. Okay, so I'll just quickly make a tree over here. This is the tree. You know what its pre-order is gonna be. Now, can you guys think how can we do it without recursion? Any thought? Like just give a 2 minutes of thought. Otherwise, I'll just tell you what will be the solution for this. Guys, any idea?
Ma'am, using while loop, will keep on going from root to the left, and then if the node becomes null, then we start going.
Come again.
Oh, so I was thinking that while in a while loop, we
Hmm?
will call root dot data and
So
then
you are
go
saying that from root will go to left, left, left until it's like,
until null.
yeah. And then what will you do?
Then mm, again come back with the data and then write. Um,
Okay.
if not null, then come back to the node dot data and then node dot write. So this way we will traverse one shoulder of the root.
Can you try implementing your solution?
Yeah, I'll try.
Because you are saying that we will go till it's null. Okay, fine. Then how will you go back? Because you are saying, see, it's an iterative approach. It's basically without recursion. So in recursion, what used to happen, you reach null, then you will call your previous function call, then you reach another previous function call, and that's where you used to traverse back, basically backtracking, right? Getting me? And but here you are saying we will reach null, but after that, is there any way you are going to go back? Vishnu, if
No,
you,
no. So I was thinking that if after we reach null, then we start going backward, like root dot
how?
data, root dot write. Yeah. If,
The thing is, when you have reached the extreme null position, how will you go back?
yeah, I'm thinking I don't know easy way
Right?
to come
So
back.
like it can be said, but it cannot be done in that way, right?
Yeah.
Okay. And now coming on to solution, which is said by Kishan. So Kishan is saying that we can calculate the depth of the tree using using the for loop till the depth. We can print the root dot data, check if left node and right node is null. We can break, else we can keep printing the nodes. But still, I am not clear, Kishan, with your complete approach. Okay, you will go till the depth. Okay, fine, but you can either go on the extreme left, you can either go on the extreme right. You can't be on both the ends. Are you getting it?
In that case, we need to have two while loop, one for the left, one for the right.
We can use the concept of level order traversal using queues. Level order traversal, okay. So you are gonna print levels.
No, I mean, I'm not thinking about level order.
No, actually, Kishan is, it won't work, right? So now, discussing the solution, it's like you take a stack, you push 2 into it, okay? Then check if stack is empty or not. If it is not empty, pop this 2 out and then insert the right node first. So I will insert 25 first and then I will push 7. Getting it? First right child and then the left child. After that, whatever is on the top, you just need to pop it. And then again, you will insert the right child, that is 12. And then the left child, that is -1. If you keep going on in the same way, you will be able to print your pre-order without recursion. Are you guys able to follow? Yes. So that is the technique here. Similar to this pre-order, you will also have in order and post order. So I don't think the implementation is needed here. Is it needed? Do you guys need the implementation here? If you explain, it will be good for pre-order. Okay. I'll explain for the pre-order and then you can go ahead and write it for the in order and post order. Will that be okay? So you guys, okay, I'll just have a text box. So you can have your class pre-order. Then what you need the explanation for, Kishan? Analysis. Like how we got to this code. It's simple, right? The analysis part here is quite simple. And the analysis here, you can say that in pre-order traversal, what you need to do, you need to first print the left, then the data. Sorry, my bad. You first need to print data, then left, and then right. Correct. So it's simple. If you first print data, it's fine. You have root, you will print root.data. But how will you first print left side and then you will go to the right side? So it's like, and it's not only like you need to print this left and then immediately this right. You need to print all the left side data and then you need to start with the right side data. So for that, what we can do, the concept was keep accumulating the right side data in your stack. On the other hand, keep popping out the left side data. Are you getting it? And similarly, if you go with the in order, what thing will you follow? Can you tell me? If you guys write the code for in order, okay, right now I told you for the pre-order. Pre-order is done. Similar to this, if you do the analysis for in order, how will you proceed?
Ma'am, I'm just thinking it. In
Mhm.
order is like ascending order, that is left data and then right.
Yeah, right.
So, so the thing I'm thinking is that um, pushing the data in the order of left and then the data, then right, and then popping out once it reaches the leaf when it is equal to null.
It's basically like in the in order, you have to go till the extreme left.
Correct.
Then you need to see if there are rights. Going to the right also, you need to check if that right node has the left further or not, right?
Right.
Are you getting it? So you can have a loop where you can check that until your root is not equals to null, you can just keep on going to the left hand side. Are you getting it? At a point where you get null, okay, that point you need to stop. You need to pop out your last pushed element. And then what you need to do,
Then data.
that is your data you need to print. Okay. And after that, for the same route, you need to go to the right hand side. Are you guys getting it?
Correct. Yeah.
So this is what we can do for in order. For the post order, what can you do?
Ma'am, once again, in order, when you go to the leaf, we do the push, then sorry, pop the leaf, and then the pop the data, and then pop the write. So
Sorry, repeat.
so in order, once we reach to the leaf of an in order traversal,
Yeah.
we do the pop of the left node, which is the leaf.
See,
Then
I'll
then
just
we
tell you what we are doing here. The analysis will be better. Okay. So see, this is my root 2. I checked if root dot left is null or not. It is not null. So what I do, I stored 2. Then left is not null. I stored 7. Then -1 is not null. I stored -1. When I check this dot left, is it null or not?
yes, it is null.
It is null. So I'll just print this. Okay. So this one will be printed. After this, once it is printed, you will see if there is some write towards it or not, right? So now you make your current root as whatever this data was. Let's suppose this was n. So n dot write will be your now current root. Now you will again insert, this is popped, okay? This is popped. 9 will get inserted here. Then you will again check if left is there, 10 is there, 10 insert. Then again check left is there or not, 4 is there, 4 is inserted. After this, if you will check, it is null. So since it is null, again what you will do, you will pop out this 4. 4 will be printed. After that, you will make this as your write, like your root as your write. Again, this is null. So what will you do? What will you do?
So here we have to go back.
Yeah, that means you will again pop out your current element. No, pop 10, right? 4 was already popped out.
Yeah, now
So 10 will be popped out. Getting it? Now for the 10, now you will make like this current data
ma'am,
dot write.
ma'am, from 4 to 10, how do we go?
The thing is you found null here, right?
Okay, then
There you are not able to find any data further on your right hand side, correct?
yes, then
So
after that,
what will you do? You will pop out the top element from your stack.
okay,
That's how you went back. Then you printed 10 and now you will make this particular node as your root again. Then you will go to the left hand side of this root. That means you will enter -5, you will enter 13. When you will check on the left hand side of the 13, nothing is there. Now you will pop 13. Clear? 13 will be popped out. After this, you will make, after this,
after that -5.
no, you will try to go to the right hand side of 13, right?
Okay,
Yeah, so now your current root will be null. It will check if the current root is null or not. It is null. Again, it will pop out the element that is -5. So -5 will be popped out and it will be printed here. After this, again, it will make the right hand side as the root, that is 8. So 8 will be inserted here. Now it will try to go on the left hand side. Nothing is there. So it will pop out this 8. Now, clear or not?
yeah,
Yeah. After this, when it will check the right hand side of it, again, a null is there. So if null is there, it will pop the top element of the stack, that is 9. So 9 will be popped out. So whenever it is finding a null, the top element of the stack is getting popped out. I hope the question is clear.
ma'am, there is one small doubt I have, is that we are keeping the tree as it is. As we are traversing, we are pushing it to a stack.
Hmm.
So
Correct.
yeah, So both are traversal, and the push and pop of the stack is in one loop, means in one big
In one go.
in one iteration.
Yeah.
Okay, yeah, then it makes sense.
Clear, no?
Yeah.
Okay, perfect. So I told you the idea of post like in order and pre-order. You try to do it for the post order on your own. I hope the analysis is clear now. Okay, perfect. Then leave the coding part. Guys, if you want to do the iterative way of pre-order and post-order, try to go on the interview bit. There you will find the 3 questions for pre-order traversal, in-order traversal, and post-order traversal. Try to complete all 3 of them. Okay, so in this specific trees, like trees are almost over now. Now we will proceed to the heap. So before that, I'll just give you few topics which you can visit. First is you can look for Morris traversal. If you guys visit these topics, you have any doubts, you can come to me, but you need to look at them on your own, because these are not like very famous interview questions, but it's like a chance of them coming in them. So I'm just giving you. There is one more, threaded binary tree. Just give a read to these topics, okay? Okay. Third is you have to look for BBSTs. BBSTs have 2 options. One is AVL trees and one is red black trees. Whatever topic we have covered is like a perfect preparation for an interview, but if you want to know more and have more knowledge on trees and all, you can visit these topics or give at least a read to these topics. I hope. Yeah, sorry.
Would you give an overview of all these 3-4 topics? Or
See, I can give, but the time is getting very much increased. Okay, so if there will be time at the end of the end when we have covered all the topics, that is DP and graph, I'll surely give you an overview. But right now, you all guys use Google, you all use some web browsers. Go visit, read, because I've already given a lot of questions explained in the class, coded in the class. Like I guess this is one of my batch where I've like actually given a lot of demos for the questions. Other students of me, if you will ask them, they are like that the demos mostly never happened. I always used to write the codes in the ID or like in the whiteboard itself. Okay. Okay, so quickly we'll just go through a topic and like just a discussion. So basically, if you are using the solution of unsorted array,
ma'am, you're going to talk about heap or something you said just
yeah,
before.
right. And that's like I'm making a base for that. Okay, so if you want to do an insertion in an unsorted array, how much time will it take? Insert. Not at specific index, just an insertion, any random, like see, it's an unsorted array, right? Any random number it is coming in.
All we are trying to do is just putting it somewhere in the array
Correct.
without sorting it. So it will be one.
Okay. How will you get the minimum element? How much time will it take to get the minimum element in an unsorted array? Okay, order of n. Delete min.
N, order
N.
of n.
So this will be 1. This will be n. At least you guys have a good analysis of these now. Okay, perfect. Next is 2 stacks. If I'm using 2 stacks, you all know that we did a question where we can find out the minimum in a stack, right? You all remember that? Okay, so if we are using that, how much time will it take for insertion? How much time will it take for getting them in, and how much time will it take for deletion? Deletion, will it take order of 1? Yeah, we are using 2 stacks. Okay. Let's suppose you have the minimum element at the bottom, that is 1. Okay. 1. And above it, there are 4, like there are 100 of elements. So if you have to get min, you know that this one will be followed till the 100 elements. So when you need to find the min, you will get it in order of 1. But for deletion, it will take order of n. Correct. Clear na everyone? So this will take 1, order of 1, and this is gonna take n. Okay, sorted array, insertion and deletion. In a sorted array, how much time will an insertion take?
Order of n.
Correct. Getting minimum.
1.
Deletion.
I think n, it has to traverse through the one.
Imagine it is an ascending order array and you have to delete minimum.
So I'm just thinking 1. The minimum is deleting minimum is 1.
Correct. Order of 1. Next is singly sorted linked list.
Singly sorted list.
Sorry, sorted singly linked list. Sorted singly linked list. Again, it will take insertion as order of n, right? Though it is sorted. You have to maintain the sorted order, right? And let's suppose any of the number comes, which is like next to minimum number, you need to shift all the remaining elements towards the right hand side. Are you getting it?
Yeah, I mean, we'll just have to put in the middle and all the elements will move towards the other side in the linked list.
Okay. Linked list is a node reaction. Okay. But still you need to traverse, right? You can't insert it anywhere.
Oh yeah, so yes.
Kishan,
we
are you
have to.
getting it? That if you have to insert it in a sorted way, you first need to traverse it and find a position for that element to insert in that specific location. Yes. Getting minimum. Why searching? It is a sorted singly linked list, guys. You will know that, okay, this is also an ascending order. You will know where your minimum belongs to, right? And delete min, again one. Unsorted singly linked list. Any place we can insert? Yes. Okay, so this will be one. Getting min, n. Deleting min, again n. In a sorted map, if it is a sorted map, how much time will the insertion take? Sorted map insertion will take order of n. Are you sure, guys?
So it is sorted on the key, and when we are trying to insert, we are inserting based on the key. So log n, I was thinking.
Yeah, right. It is log n.
Okay. And min are both 1, 1.
Clear, no? Why sorted map is taking a log n time? Correct.
Yeah, what I was thinking is it is going to take from half and then half and half like that.
Is it clear now? Okay. Getting min. Getting minimum in a sorted map. Are you guys sure? Are you guys sure that it is gonna take getting minimum? Yeah, right. For minimum, again, you need to do the same thing as you did for the insertion. So it will again take log n. Guys, remember here the minimum number. Bhuvnesh, if you have any doubt, you can ask.
No, I'm not clear. When I'm trying to get
Okay,
min,
why you said that for insertion it is gonna take log n?
so first it will search
What search?
that quick sort.
The thing is why it is gonna search, why it cannot insert straightforwardly in a certain position, or why it is not taking n times. That means traverse in the entire map and then find a position to insert. Why is it not doing in that way?
Because the input is a given element, then I have to put it at a particular place. So I have to find where to put that.
Yeah, and it is a sorted map. That means it has the data as sorted, right?
Yeah.
So to insert your element at certain position, what you need to do? You will do a binary search here, right?
Yeah.
You will find out what is the position you need to insert your element. Getting it?
Yeah. This insert is clear.
In the similar way, for getting the minimum element, it is not a straightforward technique that you can print the element at the 0th index and that will be minimum.
Why not?
Why not? Okay, how will you fetch your element at the 0th index? Like, can you fetch your minimum element in the map at the 0th
Yeah.
index?
So using get iterator, I'll get the list and then find the first element.
Okay. And you're guessing that it is going to be the minimum?
Either the first element or the last element would be the minimum.
See, whenever we are storing in a map, there is some hashing which we use. Okay. There is some encoding or some position that we use to insert an element in a map. Are you getting it?
Yeah. So if the element that is being inserted is key, then no need to do that. If we are putting it in the data, then we have to do the hashing thing.
Right. So it is a sorted map, right?
Yeah. So when I am trying to get the minimum, what does it mean? Does it minimum of the key or minimum of the data?
Obviously, you need to find the data.
Oh, then it is clear. Then it is clear.
If it would have been a sorted, what should I say? Set. How much time would it have taken for getting min?
1.
1. But since it is a map, you need to
Search the data.
take login time. Getting it? Clear now?
Yes, it is clear now.
Okay, fine. In unsorted array, we have already discussed. Okay, just give me a minute. And now we are going to see quickly a min heap, like how a min heap is being created. Okay, so you have an array.
Ma'am, what is min heap? Like, could you introduce?
I'll tell you. You have been given an array 8, 15, 6, 25, -3, 4, 17, 9, -1, and so on. Now, for inserting into a min heap or creating a min heap, you need to follow 2 techniques. One is it should be a CBT. The trees should be a CBT or should follow a CBT rule. Next is for all the nodes which is coming in. And please notice it's not a BST. All the nodes coming in should be less than or equals to the child nodes. That means child node should be bigger and the remaining nodes which you have above the child node should be, child node should be bigger and all the nodes above it should be smaller. Clear? Considering 8.
No, ma'am, it's not clear.
You will see it right now. Considering 8. 8 is inserted first, okay? Clear or not?
No, ma'am. First thing I am not clear is CBT is like a complete binary tree.
Correct.
So that means all the leaves are balanced. Like on the left one is full and right one might be empty.
It's
right?
basically like you need to complete your tree from left till right.
Right, yeah.
Okay.
And I'm not clear what is this node is less than.
Exactly. I'm saying that when we will insert, this is means for all. For all. Okay. For all nodes. Is it clear now?
Yes, ma'am.
Okay. So 8 is inserted. Next coming data is 15. 15 when comes here, since you have to follow the CBT property, it will go on the left hand side of 8 first. Next rule it has to follow for all the nodes should be less than or equals to the child node. But here child node is 15, which is bigger, and 8 is smaller, right? It is not following the property. So we will interchange them, and here 15 will come. Sorry, my bad. It's perfect. I was just reverse the property. Yeah, it's correct. Sorry, my bad. Okay, now we will see 6. So when 6 will come following the CBT property, it should come on the right hand side of 8, right? Then you will see that if you will notice the property now, the child node is smaller than the root node. Getting it? So for this purpose, we are going to interchange it. So here it will come 6 and here it is going to come as 8. After this 25, so 25 will be inserted over here. Just give me a minute. Okay. So 25 will come over here. Now when it will check, 25 is greater than its immediate parent node, which is 15. Again, it is greater than the root node, which is 6. So this is following the property, right? No need not to interchange. After this, -3 will come. -3 will be inserted over here. -3 is smaller. So again, it will be removed from here. And 15 will be removed from here. -3 will come over this place and 15 will come at this. Now this -3 and this 6 will be checked out. So again, this is smaller, removed, like interchanged. 6 will come over here and -3 will come over here. Now, does your tree looks like following the property which you have, like, which is mentioned over here? Yes.
Yes.
Okay. After the reversal, it is following, right? After this, 4 will come. So 4 will be inserted over here. Now when you will check, child node is lesser. So again, the interchange will happen. So 8 will come over here. 4 will come over here. Now it is fine. After this, 17 will come. So 17 will be stored here. And it is following the property. So nothing to be exchanged. After this, you need to insert 9. So 9 will come here. It is not following the property, interchange. 9 will come over here. 25 will come on this place. Then it is following the property, so no need to interchange. When -1 will come, -1 will come here. Not following the property again. So this will be removed, like interchanged. 9 will come over here. -1 will come at this place. Again, the interchange will happen. So 6 will come at this place and -1 will come at this place. Is the entire tree now set according to the properties which is written? Yes. And this is what a min heap look like. Min heap, basically, if you ask what is a min heap, whenever you are fetching the elements from a min heap, at the top or at the root, you have the minimum element in the entire tree. And that's why it is known as a min heap. If you talk about max heap, then max heap always have the maximum element in the tree at the top. So if someone asks you to find the maximum element, it's simply like stored all your elements in a heap, and the root element is gonna be your max element. Are you guys getting it? Yes, that's the concept behind the min heap and max heap. So interesting part here is how you insert the elements in the min heap, because it's not just about like, okay, insertions can be done, then you need to get the min heap. And insertion is not only about that you inserted -1 here. You need to insert it according to the min heap rule. Getting it, guys? Are you guys getting it? Yes. So first is insertion. Next is how to get the minimum. In how much time will you get the minimum here? In order of 1. And next is delete the minimum. So that you need to identify in how much time you're going to delete the minimum element from the min heap. So 1 is you need to figure out how to insert, and next is how to delete. Getting the minimum is an easiest task in a min heap or max heap. Clear?
Ma'am, getting min or deleting min is all both like 1 1, but
Not
inserting is
deleting min is not 1, because the thing is you can't only delete -3 from your heap. Okay. The thing is, after deleting -3, you need to figure out which number should come in its place. And if that number is coming in its place, how to resolve the other dependencies in the tree. Clear?
Yeah, so it'll be like 2 or 3 comparison. And then we can figure it out which one to put as the root.
Exactly. And for that, you need to give me some data. That, okay, ma'am, this is going to be the answer, or that is going to be the answer. Clear?
Yeah.
Perfect.
But insertion would be log n times.
Okay.
Insertion in a min heap will be like 2 times log n, because we are not only just pushing at the right location, but we are also like keep on swapping until we get to the root.
So basically, you're trying to say it's 2 times of log n, which is ultimately log n only. Okay.
Yes.
So your task today is to observe this min heap very properly and very intensely. See how much time insertion will take, how much time deletion will take. After this, we will discuss its code tomorrow, like how to insert in a min heap. Obviously, if you know how to insert or delete in a min heap, you will know how to insert or delete in a max heap. Then we will discuss few questions regarding heap, and then our tree will be done. We will discuss an interesting topic called trie. It's just an introduction, nothing much. So yeah, that's you can say complete trees will be done. Then we will move on to our DP. So my target is to cover the DP by probably in a week. So let's see how it goes.